excited to talk to you guys about 3D printing, one of my favorite topics. Today we'll be covering basic concepts of 3D printing technology, as well as our best practices for producing a model for 3D printing. At any time, if you guys have any questions about 3D printing or about producing a model, problems producing models on your printer or interest in printing models on our printers, you're welcome to email us at 3dprinting@microsolresources.com. We're also welcome at any time to come and visit our lab. We have these open house seminars, webinars about every month, but you're welcome at any time, if whatever suits your schedule, to come by. We'll show you some of the 3D printers that we have. But just to let you know, we are a 3D Systems Silver Partner, and we have access to every printer that 3D Systems creates. So if somebody needed to print something in metal, I can help you make that happen. So, again, welcome. Like I said, we're going to talk about the types of 3D printers, the available file formats, and how to produce a model. So let's start with the different types of printers and acronym after acronym. CJP, for instance, color jet printing. We have one of these printers in our lab, and we talk about that the most. It's one of my favorite technologies because it is the greenest, the fastest, and the most colorful printer on the market. Color jet printing is basically an offshoot from binder printing, or what they call binder 3D printing. So as you can see from this image, you're basically building a model based on binder applied via an inkjet cartridge on powder. So as you could see, different feeder technologies, and this isn't typical for the latest printers, but basically we dump powder onto the build bed, spray binder in a pattern just like any inkjet printer, and the result is solidified powder where the model is placed in your printing bed. So, like I said, this is one of my favorite technologies, and we have a printer in-house that I can show you, and I will show those in the office today, how that printer technology works. So when we're doing binder application, we're doing color or clear binder, so at any time. It doesn't cost any more to do a color printed model than it does to print a white printed model, so it's one of my favorite technologies. The other technology that we have in our office is called multi-jet printing. So we're literally printing or spraying the material onto the build bed. So down here is your build bed, and we're printing part material as well as support material onto the build bed through the multi-jet technology. And we have that printer in our office as well. Basically we can print white, black, clear, completely translucent after a little post-processing, as well as flexible, or what they call elastomeric material. The other technology that is very famous or very well known is stereolithography. So this is where we're using a laser beam to apply the power that solidifies the powdered material, or in this case the liquid resin material. So the liquid resin material is hit by a laser beam, and that solidifies the material. So stereolithography is first and foremost a technology. It also is referred to in the file type. The interesting thing about stereolithography was invented by 3D Systems. Chuck W. Hull was the inventor, first created this technology in 1988 as he was an engineer at 3D Systems. So like we mentioned, it's the stereolithography, or SLA, is the process. And later on, when we talk about file types, we'll learn about the file with his STL, most common file format, which is also sometimes referred to as a stereolithography format, but we'll talk about that. Another format that is very popular and very useful because of its accuracy and its speed is selective laser sintering. So we're using granular powder of different materials and hitting the material with a laser again that solidifies this material. So we have sintering and we have melting. Very similar technology. I didn't put two images because it's practically the same. Just talks about the power of the laser beam. So these materials can be of different types and different strengths depending on the need of the client. Anyway, very similar to the sintering and the melting is, actually I wanted to jump over to direct metal printing. So again, another granular material hit by a laser beam, but the direct metal printing is actually changing molecularly the material hit by the beam, which is super cool. So that was SLS and DMP, or direct metal printing. Then we're going to jump to a photopolymerization process, and you'll see these a lot. This is also another very fast technology where the material is in a liquid source and is hit from below with a light source, so that is hit automatically all at once. So the projection of the image or the layer is hit. Very interesting technology, because now they're increasing and changing this this polymerization with oxygen at the same time as the light. Really interesting stuff. Then we have selective deposition lamination. Big word for paper printing. An interesting technology where the paper is both cut and glued in processes to basically form a model. If you notice, all of these technologies have taken your geometry from your original authored software and slicing it up. So one slice at a time, or one layer at a time, is being processed, and that's why we'll talk about the printing technology in itself, added manufacturing. All right, we already talked about direct metal printing. It's a really interesting technology being used in both aircraft and automotive technology as we speak. GE is one of the biggest clients using the metal technology to print actual jet engines and jet engine parts. Really fascinating. And the most common, or the most familiar for the hobbyist, is the FDM, or some people call it FFF. Basically fused deposition modeling or fused filament fabrication, where we have a spool of material, and that spool of material is pushed through a heated extrusion head and applied one by one. What you're not seeing here is the support structure that would be necessary to print a model like this. So when you're doing FDM, you usually have two heads, one printing the support structure and one printing the model. It's also misleading to see all of this color in here, because color FDM printing is very rare, and you end up needing multiple heads or some sort of magical coloring process that colors the filament upon placing. So all 3D printing technology will require support. The interesting thing about the ones that we've chosen to support is that in the binder jetting or the CJP, color jet printing, the dry powder supports the wet. So when you're done with your model, you literally just take out, like this coffee mug, for example, and that means that the model is printed and the support material is reused. Where in FDM and technology like this, any support material that would be underneath any of these overhangs would have to be broken off and would be ended up being wasted or removed or thrown out. I know there is some talk about technology being able to regrind up that material and reuse it, but that's not very popular, nor is it very efficient. Anyway, so those are the types of 3D printers, and if anybody has any questions, you could use the chat box, and I'll address those questions later. Right now we're going to move to the file formats. So there will be a demonstration when we start talking about the geometry software and the types of methods of creating geometry. But right now we're talking about just generic file formats. This is a fraction of the file formats that are available, because there are a number of file formats depending on your piece of software. And for the most part, I can accept any file format to 3D print, because we're also very big in the software business, being an Autodesk reseller for close to 30 years. So any file format at all will most likely be able to be printed. The only thing is that that file format needs to be solid. So we'll get to the solid geometry discussion in a moment. Right now we're talking about generic file formats. So when we're talking about file formats, we have STL, we have FBX, we have OBJ, WRL. All of these individual file formats are exports from your design or your authoring software. So STL is the most common. STL is the stereolithography format, but like I mentioned, STL really stands for Standard Tessellation Language, STL. Like I said, the STL or stereolithography was the process. STL is really Standard Tessellation Language. But what's the difference? Again, created by 3D Systems. One of the reasons why we supported them ended up being a reseller is because they really understand the technology and have invented half of, if not more, of the different technologies. So STL is the most common. The problem with STL is it's white. So there is very, very rarely does STL actually have color information embedded into it. So most commonly that will end up being a white model or a model that has no color. FBX is one of my favorite formats because FBX is basically an Autodesk file format. So FBX stands for Film Box. It was developed by Kyadra and then purchased by Autodesk. So basically Autodesk generated this file format, and we use it quite a bit, translating our designs from Revit to 3D Studio Max, for instance. It's a fantastic format that contains all of the 3D information, but it also ends up creating or containing light and environment information as well. So FBX is a great format because the color and the model information is going to be embedded into one file. So other files like OBJ or WRL can contain color information, but the WRL format requires us to send along any bitmap or texture information that is going to be necessary. So WRL is another 3D file format, but has color embedded, but normally would have the bitmaps needed to be sent along. And I don't know, just another format, for instance, from things like the 3D Home Design Suite, BLD. Anyway, when it comes down to generating file formats, you have a lot of options, but the key is that that geometry needs to be solid. So top of the list of 3D printing requirements or file formats required for 3D printing is all about solid watertight geometry. So does anybody have any questions? What is a solid watertight geometry? We'll talk about it, and I'll show you some examples in the software. But basically, watertight means that the mesh is connected on all surfaces and is complete. That means that when we generate a piece of geometry that is solid, it can be created by mesh and NURBS and whatever, but the result is it needs to hold water. Now, of course, we're not actually pushing water into the file format or into the piece of geometry when we're designing it, but we have the ability to check for that type of solidification or water tightness. And I'm going to illustrate some of that in some of the applications like Revit and Rhino and Max. They all have the ability to check or verify that the geometry that you're exporting is solid. So in this photograph, you can see that there are various 3D surfaces, but some of the 3D surfaces are not closed. And you see some of the highlighted edges. So that would not print. That would be, smaller than paper thin. There is no thickness applied to these surfaces when we do a 3D surface in really any application. I'm pretty old, so some of the technology for creating a 3D surface had to be done in a clockwise fashion. You're doing three-dimensional points, and you're creating surfaces one at a time. Nowadays, obviously, we do a lot simpler geometry creation, like in Rhino or in AutoCAD or even in Revit. They're basically extrusions, where you take a profile and extrude it. So when you end up with a surface that has open edges like that, those surfaces are practically non-existent. They will not print. So you would have to close these surfaces off. And I'm going to show you a couple of examples on how we do that, or how we get geometry to be closed, to be watertight. So obviously, again, almost any piece of software can be used to create 3D solid geometry that will be printed. One of the most common is obviously our Autodesk products. Being an Autodesk reseller for close to 30 years, we're very familiar with these applications. And Autodesk is basically the creator of an ACES surface geometry. That's one of the most common file formats or geometry types that is solid and ready to be printed. Other products from Autodesk that you might be interested, or maybe get your kids interested, is 123D. If you've never seen that resource, 123D, 123D from Autodesk, literally a series of applications generated by Autodesk that would allow you to create and sculpt and make. And those are free, and those are great for get our kids involved in 3D model creation. But basically, the ones that we use every day is Revit and Max and AutoCAD, and obviously Rhino from McNeil. So when we're creating geometry in Revit, all of the objects that we're creating in Revit, for the most part, are 3D solid watertight geometry. When I make a wall, when I make a door, when I make a piece of furniture in Revit, that geometry is going to be easily exported out. And I'm going to show you a couple examples of that. So I guess let's jump into Revit right now. So I have Revit 2017 on my machine, and what I'm looking at is a model that I created in Revit. So walls, doors, windows, roofs, curtain systems, etc. And this model wasn't created for documentation. Instead, it was created for 3D printing. So as we create geometry in Revit or in AutoCAD or whatever, we're basically creating one model for documentation, one model for visualization, one model for structural analysis, and very commonly now one model for fabrication or for 3D printing. So there are certain things that I will do to this model to make it ready for 3D printing. An example, I immediately, when I started creating this model, started to use Autodesk's or Revit's displacement set tool. That basically means take a bunch of geometry and start displacing it. So each individual set of objects is not a block or a group or anything. Those elements still exist in the model as individual elements, but using Revit I can grab groups of elements and displace them, essentially move them around in a 3D view so I could see how they exist or how they interact with the rest of the geometry. So it's a very cool tool, and you can see that I can select those individual pieces and draw lines to show me where those elements would line up. So as I mentioned, I specifically created it so that it would be easily exported for 3D printing. And you can see that I've left certain gaps and certain tolerances within the geometry so that they're not coplanar. Because when I make things coplanar and I export them to 3D software, the 3D software is going to slice them up and make them available for 3D printing. Anything that touch or are coplanar really looks at the 3D software looks at it as one object. So if there's a fraction of an inch between two pieces, they will print as two pieces. Of course, every time we print our model, depending on the technology, we have to take certain considerations into that design. And you can see in here, I've left a fraction of an inch between the two pieces. But really, what I'm doing is I'm isolating these pieces. So, for instance, I grab this piece or selection of pieces, and I isolate that element, and this is something that I can easily take and export out to Revit or out of Revit for 3D printing. So, as an example, what I did was I took a piece where I've isolated just the 12th floor, and it's a segment of the 12th floor, and I've gone in and I've modified window families to remove the glass. So if I look at that window family, that RFA, there is no glass. Okay? That's just a frame inside another frame inside another frame. If I did want to print that, that would have meant that I would have had to make the glass thick enough. So sometimes I'll come through and I'll say, okay, this is a good frame, but let's double the thickness of the frame in a direction that won't take away from the design. So I do that quite a bit. Let me show you another example of something that I've done to make this model a little bit easier to print. So there's a door. The design required no door frame because when it's closed, it's the same color as the walls. But what I did is I took that door, edited the family, opened up that RFA, and made the panel as big as the opening. So meaning there is no door undercut. right? Normally there'd be a door undercut, you know, an inch or so away from the floor. But what I did is in this example, I made it so that it will literally touch the floor, maybe even overlap slightly, giving me a door panel that touches the floor. Makes it a lot easier to extract out of 3D printing. There's no overhang, there's no gap between the door and the floor. And in the technology of the color jet printing, that really makes a big difference. So I can come in here and I could blow out all of the powder and not worry about this door you know, floating in space, because there's obviously no hinge modeled, and you could tell right there it is actually hitting the wall as well. So I exaggerated certain things to make it easy to print. Okay? So the glass was turned off and the panel was extended. And in Revit, we have these things called the section boxes. I'm sure people are familiar with them. A section box is just something that's modified in the view properties to allow the extent to be controlled by a three-dimensional box. Revit is so great in its use of these things, and nowadays all I have to do is select geometry in the model, go over to the View tab and modify, and bang, I have a new selection just big enough from the selection that I had. So for instance, here's another example. Just two walls I'm selecting. So I grab two walls in the model, I go to the Modify View Panel tool, there it is, Selection Box. Now I have a new selection box that's the extent of the geometry plus a little bit bigger. Bang, that's isolation. I'm going to be able to export to 3D printing. But I would obviously need to do it a little bit bigger than that. So this was my idea. So I used a combination of section box and split floor planes to give me an extent of the model I wanted to print. Now that I have the section box limiting things like the frame of the window or what have you, that element is going to be exported. So I go over to my Add-ins tool and I get the STL Exporter for Revit. By the way, if you need the STL Exporter for Revit, you just Google it. So STL Export for Revit 2017. And there it is. It's in apps.autodesk.com. The reason why they're not making it part of the application anymore is because they have FBX and because they've made this open source. So they've taken the technology for STL Exporter from Revit and made it open source for people can go and modify it on their own. So they could download this application and manipulate it. And they even have support, revitapps.autodesk.com, and you can go and you can manipulate it. So there's one for 16, 15, you know, previous versions as well. But like I mentioned, if for whatever reason you wanted color, then you want to export FBX out of Revit. It's one of my favorites, so FBX Film Box. Let me show you how to do that. Here I am in Revit. I've isolated my view, turning off categories, using a section box, whatever. I go over to the big R, export FBX. So I'm sure some people online have Revit and probably have a building design suite. Anybody in the office have building design suite? The suite workflow is basically using FBX. So our application menu, suite workflow, bang, we take our model to max with a scene already set up and a lot of settings pre-set up in Max for interior exterior renderings. So that's where the FBX was really intended to be used, but I'm using FBX to export my model with color to a 3D printed format. Okay? So as I mentioned, I go and I take my model and I export STL. When I use STL, I'm commonly using binary. It is a compressed file format. So binary is the most common STL format for 3D printing. The ASIS surface information is an option depending on what the results and how you like it to look. Obviously, I can export link models. I can export color. So you see that STL format does have a color option. It's kind of unusual because 95% of the time an STL file will not have color information. So I don't know if people are trying to manipulate STL in the future to embed color, but every application I've seen so far, no matter how it was exported, the STL comes in white. So we can export colors, we can export shared coordinates, we can use and modify our internal units. And this is really important because when you're exporting out of any application, you want to export and provide the file to Microsol Resources for 3D printing. You want to tell us what size do you want the 3D printed output. Ideally, you would want to scale the model prior to that, or tell me what your overall extents are. So for instance, I know the overall extent of this model. It's 8 by 8 in the printed size. So when I export my model, I can be specific about how the units come across. And then when I open it up in the 3D printing. So let me know. I'll go and I'll save it. I've already actually done that. I've already done the file format, so let me show you how I open it up. So, what is all this? So this is our 3D software from 3D Systems called 3D Edit Pro. It's an awesome piece of software. It prepares the model for 3D printing. This is not the application that sends the printing job. So I use this all the time because you'll see, boy, it's not very happy today. So I'm going to have to go, hello. I think I had a little technical difficulties. What I really want to do is I want to be able to get out of this, go back to the desktop, and it's not letting me. So something horribly has gone wrong, but let's continue. What I was basically going to do is I was going to take this model out of Revit and open it up in my 3D printing software. The 3D printing software fires up and gives me the opportunity of looking through errors, just like we're doing in Rhino. So when I open a model up in Rhino, as very similar to when I open a model up in my 3D printing software, basically we run tools to do analysis on those surfaces. So one of the analysis tools in Rhino is show edges. So here I am, I type show edges, right? Opens up a dialog box. I can add objects to this analysis. But basically what Rhino is doing is it's showing me in purple where there are problems with the edges. Okay? So using this tool, I can go through and I can highlight all the individual pieces of geometry. Like this basically is one object. This was created in Rhino. It was exported out to STL to 3D print, but we had problems with it. Most of the time my 3D printing software will fix it, but I want to show you how you can prepare a model for 3D printing out of really any piece of software. You know, when you send it to me, I will definitely analyze it and check it for errors. But when you're in your 3D software like Rhino, for instance, this tool is really helpful because I'm going to be able to see where the geometry has problems. So one of the tools that I use is show naked edges, and these individual pieces are poly surfaces, but for whatever reason, they're not closed with the other poly surfaces. So this is one poly surface, this is another poly surface, but there are either gaps between the two surfaces, or there are vertices that don't line up, or what commonly happens is maybe that surface is missing. And as I showed in the image over here, missing surfaces or edges that aren't closed are going to cause problems, and that basically is where the problem occurs most commonly. So what we do in Rhino is we redraw the surfaces or we join the surfaces. So for instance, if I'm in Rhino and I say, okay, well now I know that's the problem, I'll use join, rough command, right? Join edge, and I'll grab that surface and the other surface and join the two. And then the error will go away and you can move on to the next piece. Anyway, there are a series of tools within Rhino that are perfect for this type of analysis. I'm just going to step through the other typical software that we recommend people try or that we have the most experience in. So obviously anything Autodesk we have a lot of experience in. We can help you repair the models and make suggestions for doing this. I want to go back to my presentation here. So I'm here. So Revit, Max, Rhino. Yes, we have printed models via SketchUp, but it is very common to have problems with SketchUp models. So people making SketchUp models are basically building individual faces or cutting faces or pulling and pushing faces. I always have the most problems with geometry created in SketchUp. But if you can create and unify and Boolean operations on that geometry and ensure that they're closed, then we're not going to have any problems. There's a model on our blog website that was done beautifully in SketchUp. Yeah, Bentley, MicroStation, another set of good tools for doing 3D printing. Now, we've talked about the technology, we talked about the file formats, we talked about the need for solid geometry and typical software that creates that geometry. What happens when we have errors? So when we have errors, it's most commonly open shells or face normals, meaning that when you create a piece of geometry, you see that those 3D surfaces are created in a particular way. I said clockwise before. You create a 3D surface counterclockwise, and that means that the outside surface is going to point out. So these little arrows indicate what we call face normals. So every bit of 3D printed geometry has normals. If they're flipped the wrong way or facing the wrong way, the software won't see that as being a valid closed surface. So all the normals have to be unified, and when I open and bring in a piece of geometry, that's one of the first things that it does. It looks at the overall volume of the model, determines where it thinks the center is, checks the majority of the normals if they're all facing in the right direction, then it continues with that, and face normals is very common. If you ever open up a piece of geometry in a 3D 3D modeling software and you see surfaces that are translucent, that means that the normal is facing the wrong way. The other problem that we most commonly have is called open shells. Go back to that same geometry. It doesn't have a surface to close it, all right? Or shells with errors. When we're in Rhino, here's a set of tools. Select open poly surface. Again, it highlights surfaces that are open. Show naked edges. I showed you that one already. Any edges that aren't closed will be highlighted, and you can decide how you want to remodel or how you want to join those individual pieces. Another one is called sell bad objects. So it literally goes through and it says, these objects are bad. You have to figure out what's wrong with it. In Revit, when we were in Revit and we're making modifications, for the most part, the Revit geometry is going to be completely solid and ready to print, but sometimes we have problems where the model finds errors or open shells. So before my program freaked out, I had exported this 12th floor section, exported to STL. I open it up in 3D print, 3D edit. 3D edit says I'm going to do an analysis, and it highlights, in this case, 16 shells have errors. So a lot of the errors that happen are just simply leftover polylines that aren't really intended to be a surface anyway. So these are fine. I don't have any problem with those. They're not indicating a piece of geometry that is missing. Or maybe it was the glass. Maybe what Revit does is that opening that cuts the hole in the wall ends up being an open element. Anyway, these pieces of walls were attached to the floor above. So if you recall, if you're familiar with modeling in Revit, you could tell that wall to have specific top and base heights, or you could even tell that wall, regardless of your level height, the top constraint, just attached to the floor above. So what I was going to illustrate was these individual pieces were attached to the floor above. Revit has issues with them because I didn't include the floor above, so it ended up not understanding how to cap or close those walls. So what I did in Revit is I grabbed those walls, I detached them, gave them a specific defined height, and it exported out perfectly. And that was going to be part of my demo, but imagine you saw it, and here we are with a piece of geometry that's ready to print. So this technology also does a good attempt to try to repair. So in these cases, I would look and say, well, maybe I do want to fill gaps, but I don't want to fill the window. So there are certain things that I will do and certain strategies to try to fix it. But probably the easiest is to go back into Revit and detach these type of objects. Anyway, when we're creating the geometry and we're getting it ready and we're checking for errors, you're about to send it to print. One of the first things is to make sure that the model that you're printing is at the right size that you want. So what I've basically done in the past is I've gone in and I've run checks. Okay, if this wall is 5 inches thick and I want it to print where the overall model is 1/8 of an inch equals a foot, that would make the wall, you know, 1/4 of an inch, let's say. You have to go through that and you have to do these calculations to figure out at the scale that I'm printing what is going to be my finished object. Because that is another common problem. Hey, here's my model, I want to 3D print it. And certain fins on certain curtain system, rain screen designs might be too thin. I'm not pointing my fingers or looking at anybody in particular, but she knows who I'm talking about. So that structure will come over to the 3D printing software. It's fine in the real world because that's a piece of steel. But when you scale that down to 1/2 inch equals a foot, that piece of steel is paper thin. So we want to exaggerate certain things. I had previously a link to a thickness calculator, but if you have any questions about that, or I'll work with you, that thickness calculator is missing. I went and I found it online, and I went to check the link this morning, and the website was redesigned, and the thickness calculator is gone. So I have a series of calculators that help us do this kind of thing, and actually one of the most common. I can't believe that nothing is working. My Windows is in a state of disruption at the moment. So I was about to open up the thickness calculator. It's just 1 over 4 is 1/4 inch equals a foot. You multiply that by 1 over 100. You move your decimal places, and you figure out what the calculator, what the scale factor would be. So we can use that also to figure out what's the thinnest piece, like railings and balusters, and sometimes there are wires or cables and things. So you have to figure out, I really don't want that 3D printed anyway. It would be too small. I can use it, different technology or different materials for that. So here's some basic tips. What I'm going to do is I'm going to talk about how do we optimize our creation of geometry with these particular pieces of software. So I have some general tips and tricks, right? So believe it or not, moving your geometry to 0, 0. I know it sounds kind of odd, but your geometry and its distance away from the origin has effect on the precision of the resultant geometry. Microsoft has a certain limitation. Windows has a certain limitation to the digits that represent your pieces of geometry. So scale the model to the final size if possible. Set the units and convey that to me or the team, the 3D printing team at Microsol Resources. And then what I'm going to do is I'm going to review your model. I'm going to check it for errors. I'm going to verify the scale. I'm going to provide a quote, and I'm going to confirm that outputted size, that final size with you. Anyway, when we're dealing with Rhino, what I've been told by the McNeil gurus, and by the way, we've been a Rhino reseller or a partner with McNeil for easily 25 years, right? Something like that. Maybe not 30, but I would say easily in the 20 years we've been a reseller of McNeil software, Rhino being the primary. What they've been telling us is that before you start any Rhino process, you're going to set your tolerance, right? That's basically like snap in AutoCAD. What are the increments that my mouse is going to move? When I create geometry, how is that geometry going to be created, and at what precision will my mouse and the resultant geometry be associated with? So if I set my tolerance and I also set a snap that's within that tolerance, that means that the geometry you end up creating and your mouse functions are all going to be perfectly aligned. I tell the story in my Revit class about masonry module. If you're building a building that is going to end up being a masonry building, then why not set your cursor, your snap setting to 4 inches? Everything I model will be half block or full block. Same kind of analogy when using tolerances and snapping when you're modeling for 3D printing. So then once you've set your tolerance and you use snaps and you start building your geometry, periodically use the show naked edges command to make sure that things that you're creating are closed. There are a lot of tools when you're doing poly surfaces. There are tools when you do bad objects. You can literally run a test for water tightness at the end of your, your design, and then you're going to export the STL, binary preferred, export and save. You also have an export and save as, by the way. So what I've seen people do is they're in one piece of software and they're creating geometry. They export to STL, open it up in Rhino, import that model into Rhino and do analysis, do the show naked edges, the bad objects, check for water tightness. So you can definitely import and export STL from Rhino. Then you could export or even save as STL in Rhino. What's the benefit? It depends. If you only want to set pieces out and you want to send me small components, it would be beneficial. This way I can adjust and arrange those elements in my 3D printer for best performance or best result. Because when you take a model and you apply it or situate it in the printing bed, there are certain orientations that would be beneficial. So if you export your model as one giant STL, how do I individually move pieces around for best result? Things like columns. I wouldn't want columns to be vertical because everything is going to be based on layer. That would end up being a perfect shear point. Your column's going to break. But if I lay the column down horizontally or lengthwise, the layers will be the length of the column or the height of the column. Anyway, you have a series of also plugins that are available for Rhino. So Rhino is one of the best applications for creating 3D modeling. Max and Max Design, currently only Max now it's called, 3ds Max from Autodesk. Close your modifier stack. So if you're familiar with Max, you have the opportunity of adding modifiers like bends and twists and extrudes. You want to close that, export it to 3D printing. Convert it to an editable mesh. It's a preferred piece of geometry for 3D printing. There are STL checkers built into Max, and there are also some plugins. But basically, the STL check modifier is a modifier that you apply to your geometry, and it literally will highlight all the things like bad surfaces or naked edges or open surfaces. So it's a perfect tool built into 3D Studio Max. Export the STL. You could export selected pieces, like I mentioned, or the entire thing. So within 3D systems, like for instance, if you were to get a 3D printer from us, please do, you would get these pieces of software, a 3D print software, a 3D edit software that do error checking. Okay? So error checking, checking face normals, checking open shells, all of these tools are within, they wouldn't see it anyway. All these tools are within the applications that come from 3D systems, 3D edit, 3D print. So they have some pretty good tools to check. One of the things that I've made available for you, or formally, yeah, this is in a PDF that I have. You'll get a copy of it, or you can find it on our 3D printing website. Basically, anything related to color jet printing, people call it sandstone, people call it powder. These are great tips and tricks for creating geometry. And again, that PDF is available on our website, microsolresources.com. And the PDF goes into great detail about what all this means and how to best create geometry. So there's an open surface that won't hold water, even though it's got a minute little opening here. Okay? So that won't print because of this tiny little piece. There's a little gap over there. These ideas is that basically, wouldn't it be better to actually get rid of the entire geometry underneath this house so that it was completely open? Because even though that tiny little gap, this is end up going to be filled with support material. And we don't want that. We don't want to waste material inside there. Same thing over here. This would be a complete waste. Why would we make a complete solid geometry when we can hollow it out? So what I usually require is like, I don't know, maybe an 1/8 inch, somewhere between a 1/16 and an 1/8 inch to be a shear strength structural wall in our 3D printed objects. So again, don't leave material inside your model. Design an opportunity for, recovering that material or, optimizing it. So geometry that's just a fraction of an inch away will print as two pieces. So that might mean pieces on your facade of the building would just fall right off because there's a 32nd of an inch gap. Believe me, it's happened. All right? So back to things like AutoCAD. There are some real basic tools to help make sure that geometry we export from AutoCAD comes out okay. So display silhouette set to 0, isoline set to silhouette to 1, isoline set to 0, facet res to 10. That means that your geometry is not going to, you're not going to see all those tessellations, because in AutoCAD, pieces of 3D geometry is triangulations, tessellated with triangles. So we're trying to minimize the visualization of those triangles because we don't want to obviously print a faceted surface. We want to print a smooth surface. Again, believe it or not, this is a requirement or a suggestion. Moving your geometries not only close to the XYZ, not only close to the origin, but in a positive quadrant related to the origin. And I was really kind of surprised about that, but it's a proven fact. So exporting out of AutoCAD, move your geometry so the origin is lower left. And you have STL out and all of that other stuff. There are a series of tools that Autodesk has been creating that are really helpful. So it formerly was called Project Miller. Now it's called Remake. So Remake, Recap, Within. There's all of these interesting little tools. So maybe this is no longer Autodesk Lab, so I have to fix my slide because it was another product, like a beta product. This one is really cool. It's called Autodesk Within. It allows computational algorithms to create geometry. So you might design a bracket for a piece of structure. The computer or this algorithm within the application code within would generate it in a stronger, more lightweight, using less materials. So it's fascinating. It might be something that we could actually look at. So undo that, copy that. If I go to the web and go to Autodesk Within, really a cool tool. Generative design technology. So you're literally creating geometry that would be using less material and optimized. So that they're focusing on the medical field and engineering field with this technology, but it's pretty cool. And this is the design, I think, because we can use the computer technology, to build forms based on the desired result that will be stronger and use less material. So this is a completely strange looking object, but anyway, they used a bunch of examples for like bike design and things like that. Anyway, Autodesk is definitely pushing the limit. Here's a great example. So a structural bracket normally would be solid steel in between, and this is going to be much more optimized and use less material and yet be stronger and more flexible actually, where necessary or where useful. Cool stuff, right? So again, basically what we're saying is there's a lot of technology out there for creating optimized geometry for 3D printing, and Autodesk is one of the companies that is really just pushing the limit, continuing to develop applications that are useful for 3D printing. One thing in general that they're leaning towards is the future of geometry creation, which is capture, reality capture. So reality capture means scanning or photographing. Okay, so scanning we're all very familiar. Things like LiDAR. Photogrammetry is new, so it's a series of photographs. So we're creating photographs, and we're creating geometry based on those photographs. So the first one is LiDAR, laser scanning, and Leica is a great example. They've been the inventors of this type of technology for a long time. So you go into a particular project and you scan complexities like mechanical rooms are perfect examples. How long would it take for somebody to document all of this existing information? You come in here with a laser scanner, you capture all this information, you turn that information into geometry, so that you can use in clash detection in your design. So this is just a great example. And here's another one where, you know, they're designing the new piece within the old piece. So here is combination of scanned information and modeled information within Revit. So like has been just one example of it. The other one was photogrammetry. So photogrammetry means capturing information based on, oh, I didn't want to do it in here. No, stop that. I want to do it outside, so that's Alt. No, didn't work. So this tool called Autodesk Memento allows you to both use scans and photographs to create geometry. Now that just blows my mind. So that sculpture right here was completely captured with photographs and then 3D printed.